Let's consider the simple example, sine squared x times log of cosine of x. This has a critical point at x equals 0. What happens when we Taylor expand? Sine of x becomes x plus big O of x cubed. We square that and then multiply it by the log of what? Well, 1 minus x squared over 2 plus big O of x to the fourth. We have a little bit more expansion to do, taking the sine squared term and expanding that out, and then expanding log of 1 plus something into, in this case, negative x squared over 2 plus big O of x to the fourth. Now, when we multiply these three expansions out, the leading order term is given by the product of x and negative x squared over 2. That is, we get a negative 1/2 x to the fourth plus big O x to the sixth. And we can see why we didn't use the second derivative test here, because it would have given us a 0, a fail. However, we can conclude that this really is a local maximum at 0 because of this coefficient of negative 1/2 in front of the x to the fourth. So what does that mean? Have we just invented the fourth derivative test? No, nothing that exciting. We've just done Taylor expansion. Instead of relying on specialized tests, rely on the principles. In this case, Taylor expand to see what's happening. Let's do a simple example. Consider a square of side length L, out of which we cut the four corners. We remove 4 squares of equal size and then fold at the internal edges to get an open-topped box. I want you to maximize the volume of that box with respect to what we remove. If we remove larger squares, we might get a smaller volume box. If we remove smaller squares, then we might get a smaller volume box. What is the maximal volume? Well, in this case, we'd better set x to be a variable. In this case, the side length of the corners that we remove. Then, in this case, the volume is what? Well, when we fold it up, the height of the box is x, and the length of the base is quantity L minus 2x. So the volume is x times L minus 2x quantity squared. Multiplying that out gives 4x cubed minus 4L x squared plus L squared times x. Now remember, x is the variable and L is a constant, so that when we differentiate with respect to x, we get 12x squared minus 8lx plus L squared. This factors nicely as 6x minus L times 2x minus L. And we want to factor that because we're going to compute the critical points. Setting that derivative equal to 0 and solving gives us two critical points, one at x equals L over 2 and the other at x equals L over 6. We must classify these as maxima or minima or neither as best we can. So we'll take the second derivative, which we can compute to be 24x minus 8L. Evaluating that second derivative at the critical points gives us what? At L over 2, it gives us 4L. That's a positive number, and that means that we have a minimum or a local minimum at that point. At x equals L over 6, the second derivative is negative 4L. That gives us a local maximum. Of course, this fits with your intuition. If x is equal to L over 2, then what is happening when you fold up that box? Oh, well, you're getting something with volume 0. That's clearly a minimum. We therefore conclude that the volume is maximized at x equals L over 6. But notice the problem is asking us for the maximum volume, not the value of x at which the volume is maximized. So we need to substitute back in x equals L over 6 into v to get 2L over 3, that's L minus 2x, squared times x, or L over 6. Simplifying that gives us 2L cubed over 27. That is the maximal volume. Let's look at another example. In this case, extremize the function f of x equals x cubed over 3 minus 3x squared plus 8x minus 2. And here the extremization is with some constraint. Namely, we want x to be bigger than or equal to 0. So no negative values. Let's proceed the same way. We compute the derivative of f. And we get x squared minus 6x plus 8. To compute the critical points, we're going to want to factor this as x minus 2 times x minus 4. And so setting that equal to 0 gives us a pair of critical points, x equals 2 and x equals 4. To classify them, let's compute the second derivative of f. That is simply 2x minus 6. And so we see that at x equals 2, we have a maximum with a value of 14/3. At x equals 4, the second derivative is positive, so we have a minimum at a value of 10/3. However, that is not the end. These are local extrema. The problem is to find the global maximum and minimum. When you're asked to find a global max or min, you must check the endpoints of your domain. These endpoints are critical points, since the function and or its derivative may not exist there. Let us therefore check the endpoints of our domain. Remember, our constraint is that x must be bigger than or equal to 0. Therefore, the left-hand endpoint is at x equals 0. What do we see there? Well, the value that the function takes on is -2. This is a minimum, since it is less than the other critical values that we have computed. In fact, this is the global minimum for the function. Are there any other critical points that we have to look at? Well, there's not really a right-hand endpoint to the domain, since it is unbounded. But if we tweak the language a little bit, we can say that infinity is a critical point. What is the function doing at infinity, or more properly, as x goes to infinity? Well, you can see that because the leading order term is x cubed over 3, the function tends to infinity. And therefore, we have a maximum, a global maximum, taking on the value of infinity at this right-hand endpoint. Now, of course, all of this would be fairly obvious if you drew the graph of the function. You would see the difference between the local max and the local min that we have computed, and the global minimum and maximum at the left and right-hand endpoints, respectively. Always check your endpoints.
This lecture was the best, or maybe it was the worst. You're going to have to compute a few derivatives to find out for sure. In our next lesson, we're going to turn from the concrete notion of a derivative to the subtly different idea of a differential.